Please do a voiceover.
I am. I'm going to do a voiceover after you all have gave me the most interesting script to read on the voiceover. 3.2, I am recording in voice. You can see the little numbers on the bottom there by the microphone. And if you ever see this, I'm going to just put it on stop right. That way I don't have that happen again, especially if it's a really good lecture. We're going to do the derivative as a function. When we get into 3.3, we are done with the difference quotient forever. Well, mostly done with it forever. But we're going to be done with it for quite a while. So we're going to look at the derivative of a given function. We're going to do a higher order derivative, so I'm going to do it once and only once. Once and only once. And so, again, the way that we define the derivative still is f of x is equal to the limit of the difference quotient. So like the one that we just did, if I want to find it generically, because I don't have a given a value to start, I don't have an instantaneous, then I'm going to use this definition, f prime of x is equal to. Which one of these two would you like me to do, A or B? B? All right. So I'm going to do f prime is equal to the limit as h approaches 0. Now everywhere I see x in my original function, I replace with x plus h. So this gets replaced with x plus h. And this gets replaced with x plus h. All of that represents the f of x plus h. That's all that represents. That's all I've gotten done so far. That's it. And then minus. Now this tells me right here that I am going to subtract off my original function as it stands. So minus x plus 1/2, or 1x. 1 over x. Make sure you put that in parentheses, because you got to make sure that you pull that negative through. And this thing is all over h. Okay, is there any questions so far? All right. So what I have, this is equal to the limit as h approaches 0 of x plus h plus 1 over x plus h minus x minus 1 over h all over h. Remember to distribute that -1 through. When I do that, my x's cancel, and that's about it. But I'll take what I can. So this is equal to the limit as h approaches 0 of h plus 1 over x plus h minus 1 over x all over h. Is there any questions? Okay. I have a complex fraction. I have a fraction with a fraction, which means I'm going to multiply everything by my lowest common denominator. So I'm going to look at every single term in there. This first one is over 1, so that brings me nothing. This one is over x plus h. This one is over x. This one is over 1, so that brings me nothing. So my lowest common denominator is x, x plus h, and I'm going to multiply each term by that. I'm going to multiply this by x, x plus h. I'm going to multiply this by x, x plus h, and this x, x plus h. And don't forget that denominator. Every single term will get multiplied by the lowest common denominator, so I can clear my fractions. On my first term, the limit as h approaches 0, my first term, I'm going to have nothing cancel out, so I have x I have x, h, x plus h. Nothing canceled out. My second one, my second term, my x plus h canceled out. So I have plus x. My third one, third term in the numerator, my x is canceled, leaving me minus x plus h. In the denominator, nothing canceled. So, by the magic of marker and the power of grayskull, this becomes minus x minus h. That means my x's will cancel. So what I have is the limit as h approaches 0 of x plus x times h, x plus h minus h all over xh, x plus h. Now could I have multiplied the xh through that first grouping? Yeah, I don't want to. The reason I don't want to is because I know that this term has an h, this term has an h, this term has an h. So if I were to factor out an h out of each one of those terms, I'll have a cancellation with the h in the denominator. So when I do that, I get the limit as h approaches 0 of x, x plus h minus 1 all over x, x plus h. It's all good. It's all good. You gotta watch me though, I am sketchy. You never know. Can I do direct substitution now? Yes, so I will. So this is equal to x times x plus 0 minus 1 all over x, x plus 0. So in other words, I have x squared minus 1 over x squared. Yes?
Why did you have the minus 1 instead of the minus a?
So back at this step right here, this one, what I did was I factored an h out of each term. So h, x plus h minus 1 all over h, x plus h. And the reason I did that is so those h's will cancel. Okay? How was that? Cool. Any questions? All right. Please do that first one. Is anybody willing to come up here and write on here? You don't have to give any voice, just write on here. Anyone?
Sure.
Cool. I'm gonna stop the recording, which is so you don't have to talk unless you want. Did you want to talk through it?
No.
Okay. So I'm gonna stop the recording and then. So what this student did is that he just didn't worry about the limit part. And you don't have to keep writing the limit part. This is side work. I consider this side work, right? So he put the x plus h, so he's doing the difference quotient. So what the student is doing is just focusing in on this portion of it, which is totally fine. It's the side work, and that's fine. So he took and replaced the x with x plus h and then minus the original function over h. So working with just the f of x plus h is that portion right there. So notice he didn't put an equal sign, which is exactly what you need to be doing. You don't write an equal sign because these are not equivalent yet. Okay? So then he just worked with that x plus h part. He multiplied out the x plus h part. He's still working with that part. And again, he did not write an equal sign. Cool. On the next step, he said, well, I know what that's going to combine up into. Oh, and he did actually add that for the original function. He combined up like terms in this step and put it over h. He did not put equal sign because these are not equivalent. I cannot say that this step right here is equivalent to this step right here because this step right here does not have an over h. So don't write equal sign there because it is not equivalent. The only right equals is when it is equivalent. Then he's continued on to the next step, and he said, well, you know what, an h factors out, so let's factor out an h. And then here, I'm just going to squeeze in just the limit as h goes to 0 of this and equals. And if you do that on the test like that, and you don't write equals, and you get down to doing just this portion, and I see the equals like that, that's fine. You'll get full credit. Don't write equals unless it truly is equals. So what I'm saying here is, if you have this, if you go from 4x plus h squared minus 4x squared all over h, and you say this equals the limit, please don't do that, because it's not equal, because the limit wasn't there in the first place. Those are not equal, okay? Good job, thank you. Thank you for coming up and doing that. So now we're going to talk about what it means to differentiate. So if we say it is differentiable, then f prime of a, if it's differentiable at some point a, then f prime of a must exist, okay? So if we say it's differentiable on an open set, that means it's differentiable on every piece in that set. That leads us to, if we say it's differentiable, that means it is continuous. So if it is a differentiable function, it is a continuous function. If it is not continuous, it is not differentiable. When I'm talking about continuity, I'm talking about on its domain. So if it is differentiable on its domain, it is continuous on its domain. If it's not continuous on its domain, it means it's not differentiable. Now here's the kicker. It can be continuous, but that does not mean I get differentiability on it. I can have a continuous function, but is not guaranteed. It can be continuous, but it's not guaranteed to be differentiable. Continuity does not mean I get immediately the result is it's differentiable. Here are two examples in which they are continuous functions. On its domain, there's no jumps, there's no gaps, there's no holes. But neither one of them are continuous on their domain, or not, neither one of them are differentiable on their entire domain. You cannot differentiate these on their entire domain. Can we differentiate them? Oh, absolutely we can, but we don't get to do it on its entire domain. There are places in which we have to pull out and say, at this point, it's not differentiable, even though that point is in the domain. These three examples, they are continuous, but they are not differentiable everywhere on its domain. With your partners, discuss where you think that point is, where we don't have the ability to differentiate. On these examples, they're not differentiable at 0. And this is why. If there are any sharp corners, like absolute values, it's not differentiable at that sharp corner. If the function has a vertical tangent, like the cube root of x, wherever that has a vertical tangent, it is not differentiable at that point. Yes, Max?
So does that have to do with instantaneous velocity that it doesn't exist, or that it's not differentiable?
So the way that we define differentiability is that it has to be a smooth curve, and it has to be a continuous curve. So it doesn't have to do with the instantaneous velocity. It has the fact that it has to be smooth and continuous. Now if I take a look at this one, here, this one matches the smooth and continuous, right? Right here, this is smooth and continuous. But when we do differentiation, it has to do with a slope. Right here, the slope is undefined. And that's why we can't differentiate when it's a vertical tangent. Right? And this one, how are you gonna find the slope there if you can't come in and out of that point? So we have to come in and out of that point smoothly. I'm not coming out of that smoothly. This one has a huge oscillations. It's going back and it's isolating so quickly that that's also, I'm not allowed to have differentiation at that point. So can't be a sharp corner. So it has to be smooth. Can't have a vertical tangent because the slope is undefined. It can't have that oscillation where it's changing directions quickly back and forth. And of course, it has to be continuous at that point. Yes, Sam?
So would that oscillating one be non-differentiable at each of the peaks and troughs of the oscillation?
No, because at the peaks and the troughs, they are smooth. Let's look at one of these. Let's just look at the one that's big right here. Right there, it's nice and smooth, so I can do it there. But when I get into 0, the oscillations are so minute and so quick, that's where I can't differentiate. So on either side of that point, I'm good to go, but not at that point. So going into it, the oscillations are okay, but just not right at that point. So again, I can't differentiate at a corner. I can't differentiate at a vertical tangent. I can't differentiate if the slope of the secant is changing directions quickly. And of course, I can't differentiate unless it's continuous. Those are the 3 places, or the 4 places, that must happen for me to be able to differentiate it. No corners, obviously no jumps, it has to be continuous. No corners, no vertical tangents, and no quick oscillations. So on these, I want you to determine their functions, the domains of their functions, and where you may have an issue of whether or not there's a vertical tangent anywhere, whether or not there may be a corner somewhere, or whether or not there may be an oscillation somewhere, or whether or not it may be undefined somewhere. So take a look at these by inspection and determine where you may have issues. For the first one, you ended up with a graph that looks something like this, I hope. Here's -1, and it comes in smooth, but then has a corner right there. Did you end up with something that looked like that? So where can I not differentiate this function? -1. Can I do the differentiation of the function? Oh, absolutely. I can differentiate it with the rules here momentarily in 3.3, but I can't evaluate it at -1. Differentiate it, I just can't evaluate it at -1. No.
No?
Okay, so for B, that's kind of what the graph looks like. Is there any problems on that graph? Is there a place in which I have a vertical tangent?
0.
Did you all scan in and it is at 0? Okay. So right here at 0, you have a vertical tangent. So that's the place in which when you do the derivative, you can still do the derivative of the function, you just can't evaluate it at 0. Does that make sense? Cool. So when we get into the average rates of, or the instantaneous rates of change in 3.4, we're going to get into this more heavily. If I'm given the function f of t or s of t, you might say it as s of t. If that is the position function, then the first derivative is the velocity. The second derivative is the acceleration. And the third derivative is jerk. So if you're on one of those god-awful rides that kind of spin around on like a triangle type shape, and it then spins around, have you ever been like the teacup ride or anything like that? That feeling where you go in one direction and it jerks you in the other direction? That's what jerk is. Makes you all sick and stuff. So we're going to hit that heavily in 3.4, but we do get to find higher order derivatives. Now notice the derivatives here have a 3% primes, 2 primes, or a single prime. That's one way of writing them. That means we're at the first, second, and third derivatives. They can be wrote as what we did here. But once we get to 4, we pretty much just write the number down, because it makes no sense to write 4 of them, 6 of them, 10 of them. Holy God, no. You might also see them with y prime or y of x prime. Y prime like that without the x, you just say y prime, y double prime, y triple prime, and then y to the 4th derivative. You may see them like this. And the reason this works out is because you are taking the derivative of the derivative, and so you notice that the d is where you see the squared part and the x is where you see the squared part. So if you want to know which derivative it is, you're going to look at on the d or on the x in the denominator. Those should match the 4th derivative. You're taking the derivative of the derivative. And again, I'm going to remind you that this value down there is with respect to. And I say that because at some point in this quarter, we're going to be doing this, dx dy. So we're going to treat x as a constant and take the derivative of y. So the derivative of x with respect to y. We will get there.
Calculus, even the notation has algebra.
Oh, it's so good. So I'm going to do one of these, and then I'm never going to do this again. So we're going to do this by the definition of the derivative. So the definition of derivative, I have to do the limit as h approaches 0 of x plus h, the quantity to the 4th, minus x to the 4th all over h. I'm going to come over here and do the binomial theorem with Pascal's triangle. So I have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Those are my coefficients. I know I did that fast. So this is equal to the limit as h approaches 0. It's going to be x to the 4th plus 4x to the 3rd h plus 6x squared h squared plus 4x h cubed plus h to the 4th minus x to the 4th all over h. Magic of marker. So you can see that my x to the 4th will cancel, and each one of those terms inside has an h. So I have the limit as h goes to 0. This will go down by an h, this will go down by an h, this will go down by an h, and this will go down by an h, and that will go down by an h. So I have 4x to the 3rd plus 6x squared h plus 4x h squared plus h cubed, because I factored and canceled. Do a direct substitution, I get 4x to the 3rd. That is my first derivative. This is f prime of x. Now I'm going to repeat this lovely process so I can find the second derivative. F double prime of x is the limit as h goes to 0 of 4 times x plus h cubed minus 4x to the 3rd all over h. It's good times. So this is equal to the limit as h goes to 0 of 4 times, Pascal's triangle tells me this is x to the 3rd, plus 3x squared h plus 3x h squared plus h cubed minus 4x to the 3rd all over h. See why I'm never doing this again?
Yeah.
I have the limit as h approaches 0 of 4x to the 3rd plus 12x squared h plus 12x h squared plus 3h squared minus 4x cubed all over h. My x squared cubes cancel themselves out. This has an h, this has an h, this has an h, and this has an h. The limit as h approaches 0 of 12x squared plus 12xh plus 3h, that should be a cubed, squared. Direct substitution, I get this as my second derivative. Isn't that great? And then I do this again for my third and my fourth. I'm not going to. I will make sure, look, I recorded this one with my voice. I will make sure you got deer in the headlight looks, like what the heck is she doing? I will pick this up tomorrow and I will upload this tonight. Have a great day.